All right. So if I rewrite it, then I'm going to get, excuse me, 3 over 2 root 3 is our sine. And then if I re-rationalize this, it's cleaner now. Okay. Then you get what multiply top bottom by root 3. So then you're just going to get root 3 over 3, and the 3's drop. Okay. I'm sorry, over 2. Thank you. I was looking at the 3 as I was erasing it. So, and now from there, you can figure out what angle has a sine of root 3 over 2. Your opposite being a root 3 is going to be your 60, so it's pi over 3. And then the other one would be at 2 pi over 3, because sine is positive in 1 and 2. The other way that you could have done it, it works just as quickly. Isn't that the whole thing divided by 3? Can I break it apart as common denominator? If I do that, I get negative 5 plus 2 root 3 over 3 equals negative 5 plus cosecant theta. Either way works. Either way is fine. Okay. I saw it. You know what? I didn't even think about doing the common denominators multiply really out by 3. I honestly didn't even think of that, even though that's the easiest way of doing it. I'm like, oh, I'll just divide it out and go. You get the same thing. 8. That should have been easy. Did you get pi for that?
Yep.
What was the other ones? Okay. 12, 14, 15, 16. Okay. 12. 12 is eerily similar to what we just did, isn't it? Did you do okay on that one? No. What's wrong, Mackie? Okay. I have tangent of theta is equal to 0. So when tangent of theta is equal to 0, I'm looking for an angle that has a tangent value that's 0, which means that when we're talking about tangent, it's y over x. I'm looking for the 0 to be in the numerator. Okay, so that's what I'm looking to try and solve for. So for y being 0, that means I am at 0 in pi. Does that make sense? Yes, sir.
How did you get?
Let me go. I will start over. So I have 5 minus 1/2 tangent theta is 5 minus tangent theta. Treat this like you would any other equations with variables on both sides. Pick on the little guy. The little guy here is the tangent, the negative tangent theta. So I add that one over. At the same time, I subtract the 5. So I wind up with positive 1/2 tangent theta is 0. Get rid of the half by multiplying by 2, and I get tangent theta is 0. Does that make sense? I added that over. Think of it this way. If this is 5 minus 1/2 x equals 5 minus x, if I add x, that's what I'm doing. Treat the tangent, when you have the equations like this with variables on both sides, treat it just like you would anything like that. Okay? It's much cleaner that way. Less brain work. You like that? 14, pretty quick. I get what angle has a tangent of negative 1. And then 15, I get what angle has a cosine of negative root 3 over 2. And then the last one I have what angle has a cotangent of negative root 3 over 3, so it's what angle has a tangent of negative 1 over root 3. Okay. No? Of course they do. Yeah, I have to draw it. So if I'm looking at 15, you guys okay if I say that it's going to wind up being what angle has a cosine of negative root 3 over 2? So when I go to plot that, cosine is your adjacent. So if it's negative, I'm in the second quadrant, or I'm in the third quadrant. So here's my negative root 3, there's my 2. So that means this is my 30-degree angle. So that's my pi over 6 reference. So this is 5 pi over 6, and this one is 7 pi over 6. Yes, ma'am.
How did you do 6?
I'm getting there. Oh, I wrote it over. Oh, I see what I did. Nope, I didn't. Never mind. So, and that's where I get this one. And then 16, I might have skipped a step by mistake here. Let me double check my work. Is everybody okay that the, oh, I forgot a 3 in front of, or 4 in front of that cotangent, excuse me. Is everybody okay that the 3's on both sides drop out?
Yes.
Okay. So the 3's go out. And then I'm going to subtract the cotangent from the left to the right. And I get negative root 3 equals 3 cotangent theta. Divide by the 3. So that means that if I reciprocal this, I'm going to get negative 3 over root 3 is the tangent of theta. So when I rationalize that, multiply top and bottom by the root 3. Oh, yeah, so it's root 3 over 1. I said 1 over root 3, so excuse me. So yeah, you get negative root 3 over 1. So that one is your opposite adjacent. Tangent is negative in second and fourth. If my opposite's the negative, oh, excuse me. If my opposite is the root 3, that's my adjacent. So that is going to be a 60 for both of those guys. So a 60 degree over would be pi over 3 up. 2 pi over 3. And then this would have been 5 pi over 3. Okay. So what we're going to do today really isn't anything different, except for the idea of what's called a general solution. Okay. We're going to use a bunch of the examples that we've done already, and we're going to go back to them and rewrite them in terms of what would it look like if I asked you what's your general solution versus what does it look like for one ringy dingy. What I mean by that is within one revolution. For example, this idea of what we call a general solution think of this is kind of a weird idea. This idea of what's called a general solution, I want you guys to think of it as how much pi does it take to get to another answer? Because when we deal with our solution sets that we get right now, we're looking at them as how many times they occur within one revolution. Now, when you place something in the unit circle, if I take off the restriction of one revolution, what we're looking at then is how much does it take to get to the next solution? And how much does it take to get back, and so on and so on. For example, if we just look at an answer, if we look at number 5, I'm looking at the first page up here. If we go to look at number 5 has solutions at 7 pi over 6 and 11 pi over 6. So let me just write this out here where it was what angle had a sine value of negative 1/2. We plotted it. We noticed we are at negative 1 and 2. So this was 7 pi over 6. Those were our two solutions for that problem. What angle had a sine value of -1/2? Now, if I wanted to say that was what we would write in terms of one revolution, what are your answers? List all answers between 0 and 2 pi. That's what we've been doing for the past couple of days. When we take that restriction off of the one revolution, we think about it in terms of, well, if I go from 7 pi over 6 to 11 pi over 6, is that the same distance as going from 11 pi over 6 back to 7 pi over 6? No, it's not. So as soon as I say no, it's not, then what I do is, all right, how long does it take me to get from 7 pi over 6 back to 7 pi over 6? 2 pi. So your general solution would be 7 pi over 6 plus 2 pi n. This n stands for the number of times you go around. If I go around twice, I go around 4 pi, I wind up back at 7 pi over 6, the reference of it. If I go around 12 times, I wind up back at 7 pi over 6, and so on and so on. Okay. That's what that means. Same idea with the 11 pi. How long does it take me to get back to 11 pi? Excuse me, 11 pi over 6, sorry. So my other answer would be 11 pi over 6 plus 2 pi n. That's what a general solution looks like. Sometimes. And that's, Mackie just got that one. That happens that way. If you happen to have things that are not, remember how we've had answers where they're directly across from one another? If they're directly across from one another, how far apart are they? Pi. If they're in every quadrant, how far apart are they? Depends on what the problem it is. If they're in all 4 quadrants at 45s, that makes a square, doesn't it? So it's pi over 2, pi over 2, pi over 2, pi over 2. Whereas if they're all 4 quadrants when you're like 30-degree angle or 60-degree angle, the 2 quadrants opposite each other are always pi apart, but the ones that are next to each other aren't the same distance apart. And it just depends upon the question or the answers that you get. For example, if I go to, which one had a, what was that tangent? 0? Okay, if I look at number 12. On number 12, we wound up with the tangent theta equaling 0. So that meant what angle had a tangent value of 0? Well, that meant that 0 was y and x was just something. It wasn't 0. And we found that to be located at 0 and pi. Those were my two answers. Well, this is an example of when they're equidistant from one another, to get from 0 to pi is the same distance to get back from pi to 0, isn't it? Well, we weren't talking about focus. I know it looks like an ellipse, but you don't have to worry about it. That's what I did there. Thanks, man. You set me up on that one. Appreciate it. So to get from 0 to pi, well, all we have to do is say, well, my answer is 0 plus pi n. No matter how many times I multiply pi by some number, I'm going to wind up either at 0 or at pi. And that covers both answers. It's a way of writing it the most generically as possible. Generically is not a word? General. Ah, yeah, I see what you did there. That was rather generic. I'm sorry. It's okay. We did. Let's look at. We haven't done this one yet, and I'll just write it up here. And I want to write this in terms of a general solution. The questions will ask you the following. It'll say, what is the general solution? Or it'll say, solve with it between the parameters of 0 is less than or equal to theta, which is less than 2 pi. Those are the two possible ways it can be asked. So if it says general, since there's an n in general, that means there should be plus pi n in your answer. I just thought of that. Thanks, sir. So what do you do first? Do what? Solve it. All right, so add 1, divide by 2. Okay. Sorry, I put the cart in front of the horse. Now you take the square root. And then lastly, what angle has so at this point then it's pretty quick. Which of the two triangles are we in then? We have root 2s. So if I'm in a 45, that means that my answers are going to be, they're in every quadrant for this one. And when you have a 45-degree angle, that's your pi over 4. When you have all, this is the only time that this happens. If your answer winds up being all 4 pi over 4s. When I go to ask what angle has 1 over root 2, that means my opposite's 1, my hypotenuse is root 2. I don't need to rationalize those because it's easier. It's different than what is the tangent of 60. Then you would say it's root 3 over 1 or so on and so on. Then you would simplify stuff too if you had to. But if it says what angle has this part, it's easier to work without it. So when you have all 4 45-degree angles, that means that you create a square if you plotted it on the unit circle. When you plot something that has a square, that means these guys are all 90 degrees in there. Okay? Which means each of the vertices are 90 degrees apart from one another. So the most generic way to write this would be pi over 4 plus pi over 2 n. Because pi over 2 is 90 degrees. This is the only time that you can use pi over 2. It's the only one that occurs like this. All right? It's the only one that occurs like that. We've had problems where you've had all 4 quadrants of pi over 3, but if you go from pi over 3 to 2 pi over 3, 2 pi over 3 to 5 pi over 3, 4 pi over 3, excuse me, I was doing the wrong math, and then the other side would be the 5 pi over 3. They're not all equidistant from one another, but pi over 3 and 5 pi over 3 are this. You guys look at this way. Pi over 3, wait, this was right. It's hard because I'm trying to, I'm going to draw it because it's easier. It's tough trying to know that this is your left, but this is my right. This is my left, that's your right. Yes. So if you have, if this is pi over 3, this would be 2 pi over 3, 4 pi over 3. If you have all 4 pi over 3s, they're not equidistant to each other, but these two are how far apart? Pi. And then these two are how far apart? Pi. So what happens here is that you could say pi over 3 plus pi n and 2 pi over 3 plus pi n. And that would be your solution if you have all 4 pi over 3s. It would be the same idea if you had all 4 pi over 6s. Because if you recall, when you draw out the unit circle stuff, your pi over 3s and pi over 6s, they don't create squares, they create rectangles. The diagonals are equidistant from one another. Okay, that's how that works. Oh, rectangles and squares and stuff inside circles and things. Isn't trig fun? Excuse me. All right, do this one. Take a minute and do that. So let's see how we're doing. Could I write that even easier? Pi n. I mean, good, but you know, it's okay. It's okay. All right. Sorry, I realized my handwriting was very small on that one. So I have pi over 6 plus 2 pi n, 5 pi over 6 plus 2 pi n, and 0 plus pi n. And a partridge in a pear tree. On the first day of pi, my true love gave to me an apple pie. On the second day of pi, my true love gave to me French silk pie and an apple pie. On the third day of pi, my true love gave to me a cherry pie, an apple pie, and an apple pie. What's that? I don't even know. Apple pie for 4 cups of milk, 3 cherry pies, 2 Tums, and an apple pie.
I mean, we don't want to do it, we don't have to. Pull on me.
The 7 through 10 and the 1 through 4 are all general solutions. Number 11 is not, but you can read that. Whoa. Come on. It's not dream time. Hey, just so you guys know, quiz stuff for when we get to what do you call it? Tuesday. It's stuff like this. We're doing Tuesday. Monday ones are awful. No. No, because then what if you're absent on Wednesday? Then you have to do it. Sure. I will only ever have a quiz or a test on Monday if it's absolutely necessary. It's just stupid. But yeah, everything that one packet that we had where I had you guys do the left-hand columns of the last 3 pages. Good review stuff. I don't know. Look at the first 3 pages. Try the other parts of those. These types of equations. We have one other small equation thing I'm going to show you guys on Monday, and then just kind of do a bunch of reviews on off of this stuff, as well as that packet that you guys had earlier this week. We were talking about what angle has. So that's kind of what we're going to be looking at on Monday to get ready for Tuesday. Wednesday, then we will start with what are called trig identities. We'll do that for a couple of days before we get into the break, and then we'll come back and finish the identities and do equations with identities. So we still got that'll get us. We get back from break. We have what? We come back on a Tuesday, and then we've got. I know there's the SAT day following week. So my guess is that we'll be done with this type of trig stuff that second week of April-ish, and then we'll start the graphing of all of it the following week. Graphing is actually really easy. Yeah. Graphing trig is actually, of all the graphing stuff that we do, it's probably the second easiest. Boundaries, quick graphs, chain arrangement. Yes, sir. Trust yourself. Yes, sir. Middle name. I don't remember. I don't remember. You don't remember? No, I don't. No, but you want to know my social security number? Yeah. It's like the 5 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9. No, it's 0, 0, 0, 0, 0, 0, 0, 0, 5. Oh, I was in a galaxy far, far away. Now you're going to change this again to 1. Remember, change the last one, I think. Okay? I'm just going to stop pausing real quick. I forgot to do that. I'm recording all this dead air.